Hello, everyone. Welcome to the QuIST seminar with Dr. and now Professor Souvik Biswas. Souvik did his PhD at Caltech and then is currently wrapping up his postdoctoral training at Stanford University and is starting a group next year at the University of Michigan. He has won several awards along the way. He's a rising star of both light and rising star of material science and engineering. And he also, a few years ago, got an MRS Student Award. Today, he'll talk about quantum sensing at the atomically thin limit. Take it away.
Thank you. Thanks, Marina, for the invitation, and thank you all for being at this seminar. So as Marina mentioned, I'm a postdoc currently at Stanford working on generally quantum technologies, focusing on the optical side of things. And then starting next year, I'll be developing my own group at Michigan in EECS on the ECE side. So the way I've structured this talk is to basically give you a flavor of what I've been working on and also what I'll be continuing to do at Michigan. So if you're interested, I'm happy to chat because I'm open to collaborations and also hiring at different levels. So before I dive into sort of the specific idea of quantum sensing, I want to highlight the fact that sort of quantum has been the theme of research across many disciplines for a variety of applications. So we have quantum computing, we have quantum simulation. Oh, let's just okay, anyways. So we have quantum simulation, quantum networks, and quantum sensing. And although we are at sort of the 100-year mark of quantum mechanics, this is sort of the start of where technologies are trying to outperform existing classical counterparts and also really harness the fact that something is truly quantum in nature. So for all of these applications, there are different platforms, which I'm sure many of you have heard about, starting from trapped ions, ultra-cold atoms and molecules, photons by themselves, quantum dots, solid-state spins, and superconducting circuits. Right? So my research focuses mainly on these solid-state spins that can be addressed optically, and I'll talk a little bit about how these things behave. And so, kind of the way I've structured this talk is as follows, where I first introduce what is the idea of quantum sensing, how we perform that with solid-state spins, give you a specific example of how a new class of system can be used to create quantum sensors, specifically of the type that hosts a central spin system. I will then extend how those systems can be used to make a spectrometer, but a spectrometer for noise in a reconfigurable fashion. And then I will give you a summary of what I think are the next exciting steps and some of the work I'll be continuing at Michigan. So if you think about a simple two-level system, in this case, let's say a spin, which has a spin up and spin down state, you can think of these as eigenstates on the Bloch sphere. And a classical bit usually is represented by either a 0 or 1. And the unique thing about a quantum bit is that you can take any sort of superposition, provided you maintain the length of the quantum state, and you can sort of traverse the entire Bloch sphere and create these really interesting states. So if we take an equal superposition, for example, we have 0 plus 1 over square root 2. So that's, let's say, a quantum state. We then shine a perturbation, so an external signal, which shifts one of the energy levels, let's say by omega. And then when we evolve this in time, what we get is something that looks like this. So you have a phase term in front of one of the components. And that phase term we typically call dephasing due to an external signal. So you provide a perturbation, it scrambles the phase relation between 1 and 2 or 0 and 1 and causes dephasing. So the goal of quantum sensing is pretty simple. It basically means you want to sense this phase, or in other words, omega, with high precision and speed. And if you notice carefully, the phase phi is given as a product of the perturbation strength times the time for which you evolve the quantum state, right? So then you can argue, okay, I can then just sense for a very long time, and my phase accumulation is going to be really large. So what is the problem with doing that instead of trying other techniques? That is in principle correct, except you are limited by the fact that the quantum systems, by definition, are fragile, which means they have a finite lifetime. And this lifetime sort of determines how sensitive you can be in sort of various applications, starting from condensed matter physics to timekeeping, NMR, MRI, and other medical fields. So the fact that the quantum systems are fragile is, on one hand, what enables you to do very precise measurement, but on the other hand, is what prevents you from going more and more sensitive in terms of your measurement signal or signal strength, right? So, so what we work with are these optically active spin defects, which some of you might be familiar with because Marina also has been an expert in some of these systems. In fact, our group is looking into a similar defect, but in a different host material. So this one is an NV center in diamond, where you have two missing carbon atoms. One is a vacancy site, and the other is a substitutional nitrogen atom. And typically in a semiconductor system, you have the band gap where your defect levels can reside. And in this case, what we get is a so-called spin photon interface, where you have a spin degree of freedom that is in the usually RF regime. So you have gigahertz splitting. And then you have an optical interface, which is the optical readout, which is typically in the terahertz or visible to near infrared regime. And by combining these two, you can build different ways to engineer qubits for different applications. So in our case, what we like to do is shine light. And when we shine light, we see that there is absorption, and then there is also emission. So for example, this was an experiment done in room temperature in our lab, where we have really dense NVs in diamond. So it's a thin film of diamond with lots of nitrogen vacancy centers. And we shine green light on it. And you can see this glow even by eye without any spectrometer because of how bright these defects are. So these defects have different properties, and we utilize them to understand how they're useful for different applications. So in terms of sensing, again, coming back, how we operate is, let's say we start with a state which is, let's say, the up state. We initialize our qubit. We then create the superposition state. In this case, I've just dropped the square root 2 for simplicity, but it's obviously preserving the length. Once you have the superposition state, you let this evolve over time. For time t, as I mentioned, you acquire this phase. This is the dephasing signal proportional to your omega and t. And finally, you transform this in sort of a sum and difference of the two respective eigenstates. And then you basically measure the statistics. So once you do this experiment many, many times, you get a probability distribution of how many times you're going to get the up state versus down state. And when you convert that probability, you basically get your readout statistic. So that's how you measure this protocol. And one thing I should mention here, that this is not really unique to sensing in many ways. In fact, it is a very universal tool that people use to characterize their devices in quantum computing, quantum simulations, and so on. So this is a very powerful technique for, in general quantum engineering, for characterizing the readout and the fidelity of your qubits, right? So as I mentioned, increasing the time leads to better sensitivity, but you are limited by the finite lifetime, or in other words, the coherence time of the quantum sensor. So obviously, we want to increase this coherence time. So we want as long of a T2 as possible to have the best sensor. And the reason why that's the case is if you look at this formula for sensitivity, it goes as the inverse of a factor C, which I'll discuss in a little bit, and square root of T2. So longer the T2, the lower the eta is, which means that you're able to detect a really low signal. So that's kind of your goal. So that's one aspect of building a quantum sensor. The other aspect is the readout. So as I mentioned, whether you're reading out the spin up state or spin down state, it's very important to have high confidence in whether it's a spin up or spin down, because that's going to determine the fidelity of your readout. So in this case, what I mean by this readout contrast is, imagine that if you're measuring the experiment or repeating the experiment many, many times, and you have your two histograms overlap each other, which means you basically have no distinguishability between the two states, as compared to this case, which is a single shot readout, where you have clear distinguishability, and you can tell if there are more photons than this threshold, you're in the upstate, and vice versa. So you want to be in that regime where your readout is good, and that's sort of the maximum value this can take, which is the readout efficiency. So once you're at that regime, you can then get really sensitive state-of-the-art quantum sensors. So how do we actually sense some of these signals? So when I talked about a sensor being exposed to some perturbation, I assumed that it was a very fixed frequency, well-defined omega. But in reality, what you have is random noise. You have many frequency components starting all the way from like lower frequencies to higher frequencies, and it's usually a spectrum. And it can also be different kinds of noise. So it can be an electric noise, it can be a magnetic noise, thermal noise, and so on. So how do you develop protocols to probe the spectral response of these systems? And how can you distinguish between the two regimes? So one of the simplest ways, and again, I'll describe this later on in details, is to use what is known as a lock-in detection. So often in lab, when you have very low signals to work with, you use a lock-in detector. So you have a chopped light source or a chopped electrical signal, and you use the lock-in to detect at that specific frequency, knowing that the response is only going to be dominated by that signal, right? So that gives you higher efficiency in detecting some of those weak signals. So in this case, we can design protocols to map out the entire spectrum of noise, again, with these quantum sensors. And this has been shown to be useful for many applications, starting from detection of spin environment, optically dark spins, as well as sensing spectral responses of molecules and proteins and so on. Okay, so how do we quantify what sensitivity and resolution we want? So there are different ways of doing quantum sensing. As I mentioned, we are using color centers, but there's also vapor cells and force microscopy. And what you see on the y-axis is magnetic field over a bandwidth. And you want to be as low as possible here. So you want to detect the minimum possible magnetic field that's produced by an entity. And you also want to maintain good spatial resolution. So obviously, vapor cells, because they're so large, can detect really low fields, but they're not able to maintain the resolution needed for nanoscale sensing. So one thing that you see from this plot clearly is that color centers actually span a very good range where they have decent sensitivity and also spatial resolution. And the reason that happens is because these are very tiny objects. These are literally like single atom species that are missing from the lattice. And you can pack a lot of them together, where you can also benefit from the Tiki enhancement in the light collected by a square root n factor, right? So the goal would be, can we build color centers to be even more sensitive, and can we push the sensitivity further down? Now, the challenge with color centers is that when you sense something, you want to be close to what you're sensing. And why is that? Because we know that any sort of electromagnetic field, so let's say a magnetic field from a point dipole follows as 1 over r cubed. So the further I am from what I'm trying to sense, I'm going to have to work extra hard to be able to sense the same object. So I want to be as close as possible, which means that if I have a device where my sensor is sitting 30 nanometers from the surface, and I bring in an external protein or a molecule or something else, it's way easier to sense when I'm 30 nanometers away compared to when I'm like 30 microns away, right? But the challenge then becomes surfaces are generally bad. So those who are material scientists or device engineers know that cleaning surfaces is really hard. And that's why people in Intel and TSMC have worked extra hard to passivate surfaces and create encapsulation layers with very careful ALD techniques to get to the properties of, let's say, transistors or photodetectors and so on. And so the same problem exists for quantum sensors. You generally have surface adsorbates that have spin properties that are really bad, and that kind of dictates the decoherence processes. So here you can see a plot of entry centers, where as you get close to the surface, which is given by the depth, your coherence time decreases. See the strand, and that's not really good, right? So then the question actually comes, how do we get rid of surfaces? So, I mean, of course, you cannot get rid of surfaces, but one option is to work with completely passivated surfaces. So 2D materials, for example, are these van der Waals systems where layer by layer they're assembled and held by van der Waals forces. And each layer is completely chemically passivated, so there is no dangling bond, so to speak, which means that there cannot be foreign adsorbates just sort of hovering on the surface for the most part. Right? The other advantage of using these materials are that they are atomically thin, which means I can approach my sensing target, with even an angstrom level accuracy and distance. And because they're van der Waals materials, they can be integrated with any substrate. And just like any other system, the choice of color center is quite wide, and you can choose any sort of arbitrary species for doing these sensing. So what is the material that we work with in our system? So this I mentioned that, one of the motivation is to get rid of surface. So the material that we work with is hexagonal boron nitride, and thus far it has been shown to have a lot of applications starting from sensing different modalities like temperature, strain, magnetic fields, as well as the ability to study condensed matter phases, because graphene naturally fits with boron nitride, and you can create these exotic condensed matter phases to be able to measure some of those properties. So there are different kinds of defects in HBN. I won't go into the details of the two, but the basic difference between these two species are this is a missing boron atom from the boron nitride lattice, and in this case it's a substitutional defect like an NV center. These are typically carbon-based, not very reproducible, which is kind of the problem in the community, whereas these have been well reproduced and has been quite popular. The only downside of these boron vacancies are that they come in ensembles because their emission is on sideband assisted. But that's a very subtle detail. But the idea is that these missing atoms create sort of the qubit that we need for doing our operations. So for the rest of the talk, I'm going to focus mostly on the left side style of defects. So this is how our device looks like. So we have these boron nitride flakes or devices on a microwave strip line, which is usually made of either a superconducting metal, if we can cool it down low enough, or a resistive metal where we have to live with the heat dissipation and thermal engineer the sort of surroundings properly to get high fidelity gates. And the blue sort of spin forms the central qubit or the central spin, and then is surrounded by many other spins, which are either nuclear or electronic spins, and can be either optically bright or dark. So that's just sort of the legend. And the question we ask is, in this sort of messy system, is it necessarily obvious that such a messy system is bad for quantum sensing? I mean, typically people would say you need a clean system for sensing, but in this case, we argue that we can actually engineer the system to be clean. So again, kind of zoom in on the structure, and this is the optical and the spin interface. So you shine light, so it's very much like an NV. So you shine green light, you get red light out. It's a spin 1 system. You have the spin-dependent photoluminescence property. So your ground state, when it's 0, it's bright. When it's 1, it's dark. And you can apply a magnetic field to sort of split the states using the Zeeman shift. So that's kind of, standard. And you can then do ODMR or magnetic resonance spectroscopy to see the two resonances at F minus and F plus. And you can then define your two-level system to be, one of those transitions. Well and good. Okay. So now let's see what this boron vacancy central qubit can be, made to do. So I talked about the Zeeman shift, which is, obvious because it's a spin 1 system. You apply a magnetic field, you see 2 lines. So these are the 2 lines that go. So this is the +1, this is the -1. Over here it flips because you go to 0 energies. Anyways, so this is all well and good. So this lets you sort of calibrate the Zeeman term in the qubit. But what happens when you apply a magnetic field in the off-axis direction? you see something completely different. So you see, instead of those linear lines, you now start seeing parabolic shapes, and you actually see merging of the shapes. So you go from having, kind of 4 lines to 2 individual lines that are separated by certain energy. So the question is, what is exactly happening and why there is this weird behavior? Well, if you do the math for these systems, because it's a spin-1 system, you actually see that the eigenstates no longer remain as plus and minus 1. Instead, they hybridize. So what you get is equal and even and odd superposition of the 1 and minus 1 state. Now, if you recall your quantum mechanics, the magnetic moment of such a state has to be 0 because you have 1 and minus 1. Which means now the qubit is no longer sensitive to magnetic noise. It is only sensitive to electric noise. So that's kind of cool because you take the same spin ensemble or spin qubit, and by addressing the states differently with external magnetic field, you can start picking up different kinds of noise, right? So this is kind of, in some ways, programming the qubit to be sensitive to different kinds of noise. And I'm going to show you how this is useful to do certain things, for example, study the system by itself. So the first thing that the qubit sees are these nearest nitrogen atoms. So these are nuclear spins, the red 3 entities. And those usually have some sort of nuclear back action, which is called the hyperfine interaction with the electron spin. And when you do the same experiment in the presence of the 2 different magnetic fields, in one case, what you get is, you're picking up magnetic noise. So you get 4 distinct lines in your spectroscopy, and those 4 distinct lines come from the fact that if you have 3 spin half particles, you can arrange them in 4 different combinations. So you're going to have -3 half, -half, half, and 3 half, right? But when you turn on the magnetic field in the off-axis direction, that's where everything kind of, goes crazy. So you get a bunch of these transitions that are mostly dominated by a complex tensor that is given by the electric light interaction. So now, it is a bit confusing because they're both hyperfine interactions in some sense. They're both magnetic in nature, but the fact that they couple to different eigenstates or eigen operators of the spin, they are treated differently. So in this case, it is amagnetic light interaction. In this case, it's electrical light interaction. So, okay, well and good. So we can kind of create this like rich structure, but in the presence of instrument limited and also sample limited resolution, we are not able to resolve these lines. So is there a way to do a tomography of this whole tensor while still being in this regime? And the answer is yes. And the way we do that is not doing static spectroscopy, but we do time domain spectroscopy. So how do we envision that? So you can imagine that these 3 spins act as an effective magnetic field that is dependent on time. So it's kind of like an AC noise. And you can say that, okay, so my external field and the hyperfine interaction together create an effective field for my spins. So what will happen is because of this time-dependent noise, you're going to have what is called a Larmor precession. So your spin is going to precess around a certain axis that is given by sort of the quantization of the sum of these 3 nuclear spins. And indeed, what we can then do is use this lock-in technique, which people also refer to as spin echo, where if you look at the plot on the left, what you see is spreading and closing of the phase of the qubit. So what happens is, if I prepare my qubit to be pointing along the equator, and I let it evolve for a certain time, it's going to spread out. And after a certain time, I flip it onto itself. So it's going to close back onto itself and then get projected back to the other state. So if I can do that perfectly in resonance with this Larmor frequency, I should be able to see its signature in time domain spectroscopy. So if I do that, in this case, I'm measuring coherence as a function of time. Coherence is just sort of the population. So 1 is up, 0 is down. Or you can equivalently think of this as like, being populated in the superposition state versus losing all the population. Anyways, you start seeing this resonance, right? And if you model the resonance as a product of these 3 spins from the nuclear sites, obviously you know the symmetry because it's a 120-degree triangle. You can back out very nicely the entire Hamiltonian of the system, which was previously not done. Right? So people knew about the out of plane component, which is sort of the secular approximation, but we for the first time showed that you have very strong actually memory-like resources also in the other direction, so you can reconstruct the whole Hamiltonian for the individual nuclear spins. Now, why is this interesting? It's interesting because if you think about the microscopic processes that's happening along, so at 0 time, or let's say very short times, you initialize your spin. So you have the electronic spin initialized. At the first resonance, what happens is there is interaction between the electron and nuclear spin, and you transfer some of the population from the electron to the nuclear spin. So in some sense, it gets entangled partially with the electron spin. At a later time, twice the time, it gets disentangled back. So there's a back action onto the electron spin where the population gets transferred again. And this in principle continues forever until like there is complete dissipation into the bath, right? So this is interesting to think about, because this kind of time domain spectroscopy can both give you full tomography of the system and also allow you to study kind of very interesting properties such as anisotropic Zeeman shifts and so on, as well as give rise to protocols for creating gates. So you can use the electron spin to talk to the dark nuclear spins by creating these electron nuclear gates. Now, I said that in principle, those oscillations could have gone on forever, except that there is some late time dynamics. So what sort of sets this late time decoherence processes? So in this case, we basically use noise spectroscopy to improve the sensitivity of the system and also understand why we don't see sort of infinite oscillations of the system. So let's imagine now, again, going back to sort of that picture where we have these two-level systems. In this case, you have a simple eigenstate 0 and -1 for a magnetic field out of plane. And in this case, you have the mixed state, let's say n minus, for a magnetic field in plane. And we have our qubit pointing along the equator. So we have, as usual, we're waiting for it to evolve in time. And what's happening in this case is as it evolves in time, in these two scenarios, it sees two different noises. So in this case, it sees a magnetic noise. In the lower case, it sees an electric noise. And finally, we read out what is the effect of such noise on the qubit itself. Right? So this interrogation scheme is basically similar to the lock-in detection that I talked about, where instead of doing a single pulse of the qubit, so instead of flipping the qubit once, you flip it many, many times. So you do this for n times. And if you think carefully, this looks like a periodic series. And in Fourier space, any periodic series is given by in periodic series in time is given by a peak in frequency. So if you repeat this, flipping of the qubit back and forth, you're going to create this delta function in frequency. And as you change the periodicity of these, flipping back and forth, you're going to move where this peak stands in frequency space. And as you move the peak, up and down, what you're going to get is you're going to pick up noise at different frequency components and reconstruct the entire spectrum of the electromagnetic noise. So if we do that for the two cases, the magnetic noise and the electric noise, what we see, and I'll explain what these plots mean. So first of all, these plots are coherence as a function of time. What that means is how long it takes for the qubit to completely lose all its coherence. So here you can see at low times, the coherence is 1, and slowly it becomes 0. And as you do this periodic repetition of the pulses, you are able to fight out the noise. So why you're able to fight out the noise is because you move that filter function, or this delta function, to higher and higher frequencies. And we know generally noise, let's say, has a 1 over f or 1 over f the alpha behavior. At lower frequencies, noise is going to be higher, and as you go to higher frequencies, noise becomes lower. So now if I can push my Fourier peak to higher frequencies, I am less sensitive to noise. So if I'm less sensitive to noise, my qubit is protected for a longer time, right? And that's what you see. So as you do these so-called dynamical decoupling sequences, you can extend the qubit to live much longer. So here you see it decays within like a couple hundred nanoseconds, and all the way, if we apply around 2000 pulses, it goes up to 0.1 milliseconds. So this is quite exciting because for the first time, 0.1 millisecond coherence was achieved in these tuning materials, which is definitely I would say like a milestone for the community as a whole, because there's a lot of skepticism about these materials and their quality and how it compares to, let's say, solid state systems like NVs and diamond. And so this is definitely an encouraging step for the whole community, that we should look more into some of these materials and try to improve their properties. In addition, what you see is a very different functional profile between the two magnetic field cases. So in one case, you just see a monatomic decay. And in the other case, if you recall the resonances we had from the nuclear spins, these resonances start to, kind of appear at later times. And in this case here, if you did an even finer sweep, you would start seeing many, many of those oscillations. And essentially what this tells you is that, in both cases, you are able to fight out the noise by pushing the filter function to higher frequencies. The magnetic noise is lower than the electric noise, which is why these qubits live much longer compared to this qubit. It also implies that in our sample, we have a stronger electric field coming from somewhere. If we now look at the coherence time as a function of the number of pulses, we see that they both increase sort of sublinearly, but in one case, it's a bit faster than the other case. And that confirms the fact that indeed magnetic field noise is weaker than the electric field noise. Now, why is this, beyond the fact that the coherence time is the longest, why is this also exciting? It is exciting because that lets us figure out what noise exists in the system and how we can very judiciously design pulses to back out the noise. So if I now go back to this picture of a random noise and flipping the spin back and forth, and now again, I assume simplistic single frequency AC noise, there are certain things that limit me in detection, starting from both what type of noise exists, as well as what is the phase of this signal. Why is that? The reason that is important is because generally in a system, there is disorder. So if I look at the distribution, any Gaussian distribution, counts versus, let's say, detuning, I'm going to see a spread. So if I told you previously that there are many, many spins in the system, each spin looks a little bit different. It can be different in terms of energy, it can be different in terms of phase. The reason it is different is because it's a real system, it's a lattice, has a lot of defects, has Oberhausen field, for those interested, which creates a Gaussian distribution of these spins. Obviously, the most probable ones are, let's say, at zero detuning, but there is going to be a spread of the spin energies. When that happens, let's say I apply an electromagnetic pulse or a radio frequency pulse to flip a spin from this way to that way. So if I have 1,000 spins, maybe 100 of those would flip the right amount, but then the 900 and the 450 on this side and the 450 on this side would not flip exactly the same amount. Which means that if I said my quantum system underwent a pi phase shift, it is not exactly true. So that's the first error. So I can quantify that by looking at what is the detuning, so as in like how much detune each spin is from its neighboring spin, compared to, let's say, in this case, I compare to the Rabi frequency, which is basically how fast I can drive it. And I notice in these two cases that if I send in an AC signal, let's say FAC at time t naught, which is at normalized time t naught over here, my choice of phase of these pulses determine how accurate I am. So let's say if all of my pulses are along the same phase, so let's say I apply a pi pulse along x direction, so I just keep applying along the x direction, what happens is all the errors start adding up. So you have buildup of errors, and very quickly, for even the smallest distribution in your spin ensemble, you develop an incorrect sense. So you start to sense the wrong frequency. So you should be sensing, somewhere here, but you get this parabolic dispersion. And that comes from the fact that your errors start building up. Now, if you flip the phase in a judicious manner, in this case XY8, which is you apply the first pulse at X, the next one at Y, X, Y, Y, X, Y, X, you start correcting for some of these errors because of the conjugate nature of the pulses. And you can see that even for large spread in your Gaussian distribution, you can maintain the correct frequency with much higher sensing depth. So if you look, these two plots are both plotting coherence. In this case, it's going all the way to -1, meaning the spin is completely flipping. In this case, it's going to half, meaning it has reduced spin. So that's number one. And that's the first error. The second error comes from the fact that the control itself can be wrong. So I might think that I'm applying a pi pulse, but my instrument might be outputting something like 1.15 or 1.25. So I can quantify that by saying pi plus epsilon. And I can also study how these phases can add up or cancel in terms of the detection fidelity. So in this case, if I have, again, the same direction pulses, all of them are adding up. So you get this weird chevron-looking pattern, meaning there's only a limited window of error bar that you can operate in to have high fidelity or as in like good detection. Whereas if I now flip the phase rapidly, I can have a much larger window to operate. So combined, this tells me that when I'm doing quantum sensing, people naively just say, oh, I see a dip in my signal, and that's sort of my actual frequency. That's not the case, because you can obviously be fooled by these two kinds of errors. One is disorder, the other is control error. So it's very important to note that these two types of errors can limit your sensitivity. So in a real system, what we have is both, right? So we have a disordered system where you have a bunch of spins that are kind of like spread out that creates this inhomogeneous bonding, and we also have errors coming from these pulses. And together, their effect is quantified as a tilting of the effective rotation axis. So here again, we sort of show that by doing the flipping sequence, which is XY8, we are able to maintain good sensitivity, whereas in the same phase, we lose sensitivity very quickly. So now, this is again a mathematical detail where essentially we say that there is some relation between the coherence we see and the noise spectrum. So I won't go into that because it's a little bit involved. But essentially what we can then do is, if you recall the measurements before, when you saw similar plots, coherence as a function of time, now you will see that the plots look a little bit different from the blue ones before. And the reason why that's the case is, in this case, the phases were flipped during the measurement. So you had a flip, XY8 style decoupling measurement done, which, as you know, is what you should be doing for noise spectroscopy. And once you do that, you can then back in this relation. And what you can do without loss of generality is assume that the noise is, sort of piecewise represented by this formalism, where you have certain cutoff frequency, and you have a strength, and you have a scaling. And then you can start to reconstruct the noise across different frequencies, and then you will get something that looks like this. So this roughly matches these profiles, and obviously this is not the final result. This is sort of illustrating the idea. Once we optimize this, in this case, we use machine learning, blah, 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 to figure out what the exact noise looks like. And it looks like something like this. So at low frequencies, you have roughly 1/f noise that is coming from surface things. So even though I promised these are surface free or passivated, there's still some surface effects that come from imperfect fabrication. So that's something we need to know. And at high frequencies, we're dominated by Johnson noise, which comes from the fact that you have metal close to your space. So, in theory, if you can eliminate these two effects, you should be able to suppress the noise even further, and you should be able to engineer your qubits to be even better. And we did a bunch of theory, and were able to match all our T2s with the theoretical models for surface things and Johnson noise. But future interesting work would be, can we do because Johnson noise is temperature dependent, can we do temperature dependence of this noise and see this sort of tune and get a better grasp of the origin of this, and also study how implantation density, as in how many emitters we have implanted on the surface, and how that affects sort of the low frequency component of some of this. So that's going to be some of the future work. A very exciting outcome of this work is, if you recall one of the plots that I showed before, where we had sensitivity on the y-axis and depth or resolution on the x-axis, and I said we want to be as close to the origin as possible. So here I have shown some state-of-the-art examples where the blue cases are NV centers in diamond, and the red dots, stars are HPN or some of these 2D materials. So obviously, you can see that these really deep NVs are amazing. But again, if you think about the amount of work they have to do to detect the same magnetic field at such depth, you can easily see that even though my sensitivity is 10 to the minus 11 here at a depth of about a micron, I'm still not able to resolve a single electron spin, let alone a nuclear spin. Whereas if I am at 10 to the minus 7 at around 10 nanometers, I'm easily detecting a single electron spin. And same here, I'm below the threshold of the single nuclear spin. So it benefits you to be, kind of towards this end of the spectrum rather than this end of the spectrum. And that's what we tried. So in this work, we took one of the thinnest 2D samples, and we measured, sensitivity in 2 different ways. Again, without going into too much details, this is a slightly different way of calculating sensitivity by accounting for some of the system imperfections. And this is the raw measured sensitivity. And in both cases, you see, first of all, it outperforms any of the existing HPN systems. And it also puts us, very much in competition with some of the NV centers, with room for obviously lots of improvements, because as is, we haven't even touched any of the surface or done some passivation or device engineering. So that's very exciting. And then, obviously, this has been a team effort. So my advisor, Jelena Vučković, has been mildly excited about this work when it started, and is now, quite excited about the prospects of HPN as sensors. Junhee Choi, who's a new faculty at Stanford, who's also coming from NV and AMO background. Giovanni, who was here a few weeks ago, and a few other people who have been instrumental in this work, along with collaborators from different universities, such as Purdue, Washington, and Kansas. And the work was completely supported by Department of Energy. And moving forward, some of the interesting ideas that we have to make these qubits better would be to bring in some sort of hardware engineering and very specific control. And so some of the ideas that would be interesting to explore would be, can we use strain and device control to better understand both the decoherence mechanisms as well as suppress certain channels? For example, strain to suppress certain phonon channels, device to suppress certain electrical channels, as well as optimization using different techniques such as inverse design, machine learning of counterintuitive pulse sequences that are not equally spaced to target certain frequencies of noise. So for example, let's say you want to develop a quantum sensor that is only sensitive to a certain region of the spectral window. You can start to play around with these pulse sequences and make it only sensitive to that while decoupling the rest of the systems. The other exciting thing about this system is, very recently, for those of you who have been interested in the field, there was a demonstration from Harvard on spin squeezing, where basically, if you have a tightly bound, distribution of spins in space, these spins can interact amongst them. So similar to nonlinear optics, we can have, a square term. Similar to E squared, you can have an S squared term. And that spin interaction can create essentially a distortion of the distribution of your spin uncertainty. So instead of having a uniform, your Heisenberg uncertainty delta x delta p, in this case, a circular distribution, you can spread it out along certain dimensions, and the amount of spread out you can suppress is called squeezing, and this gives you, metrological gain, as in it really harnesses the fact that it's a quantum system that is entanglement between the spins, and you can sort of get an even higher performance. Now this was very challenging in NV because it's a 3D system, so they had to work extra hard to create this really thin layer of 2D in the NV, and even then it's quite thick, has a lot of positional disorder. It has a lot of quantization disorder. So you can see some spins are this way, some this way, some this way. But our goal is if we use this HPN, all of the spins point in the same way. It's intrinsically 2D. So you should be able to create, a very strong spin squeezing system and show, tremendous metrological gain. Okay, so the last 3 slides are a bit of an advertisement. So, feel free to leave if you're not a prospective student. So I'll be starting my group at the University of Michigan in Ann Arbor next year. I'll be in the College of Engineering and ECE department. So here you can see the North Campus, which is the College of Engineering, the tower, and then the ECE building. And it's a very fun department to be in because you have not only some of the best engineering programs, but you also have access to state-of-the-art cleaning stuff. So if you like building devices and fab, you can have access to state-of-the-art e-beam, etching, deposition, and so on. In addition, you can also be part of the Quantum Research Institute that has been fairly new. So you can contribute to the growth of the quantum community. And it also has one of the strongest ultrafast optics program, as well as some of the strongest lasers. So if you like shining high power laser materials, that's a very interesting place to be. And the faculty panel for ECE usually has a mix of circuits, devices, quantum materials, and so on. And pretty much there is no boundaries, so you can be in the ECE department just like any other place and work with physics people, chemistry, and so on. And it's a very fun atmosphere to be in because is one of the also unique facts about Michigan is that even though it's maybe I shouldn't be saying this, but even though it's a public school, it operates like a private one. So there's like less bureaucracy than usual. So maybe sometimes things go quickly. As a student, you might relate to that if you order things on Thor Labs pretty frequently. If you like a nice college town where you have also access to lots of art, culture, restaurants, food, biking, kayaking, and a bit of snow, then you, I think, would have a great time for grad school or any other experience in Ann Arbor. And finally, some of the research directions that I would be pursuing in the group, obviously one is quantum sensing, where I'm interested not only to develop quantum sensors for magnetic fields and electric fields, but eventually for a lot of bio applications where we can do high throughput label-free detection of DNA proteins and so on, and make on-chip devices to create that. In addition, I'd also be looking into 2 other directions based on my postdoc and PhD work. So one of them is looking at quantum simulations, where the idea is, can we use interactions among spins and light to realize interesting and exotic states of light and matter. So for instance, looking at photonic cavities where many spins are interacting across the cavity, or for example, the spin squeezing project where the spins are interacting directly, and can we create exotic states out of that? And finally, a little bit more on the device side, I'll also be interested in exploring new materials for making functional devices that would eventually be useful for creating interconnects for these quantum devices. So for example, can we make photonic interconnects? Can we make electro-optic modulators? So yeah, we are part of I'm part of the ECE as well as the Quantum Research Institute, and also honorary physics. So in case you want to apply to the physics department, we have a bunch of fellowships from the department that would support you for 2 years, I think. And we also launched a new initiative for grad students for the James New Fellowship, which is roughly a total of $55 million. So there's going to be a very good support for the first 3 years of your PhD, and then it gets renewed if you do well. Anyway, so if you're interested, or if you know people who are interested in pursuing any of these directions, or in general photonics, quantum, I'd be happy to talk to them. You can either reach out to my email or come talk to me. And yeah, thanks for the attention.
Thank you, Souvik, for an excellent seminar. Floor is open for questions. Liam?
What in the like section where you're talking about photons, you're saying that these sensors are label free. What do you mean by that?
Yeah, so in this case, label free is really like a bio term, where basically the idea is if I want to detect a protein or let's say a biomolecule, typically people use some sort of labels or markers that they associate with this protein, which binds onto this protein. And based on how that label performs, you are able to read out what protein this is. In the process, sometimes what happens is this attaching of the label is a very slow process. Sometimes it's not reversible, which means you end up damaging the protein. And it's not a very high throughput process. In turn, if you can do it label free, as in you don't need any sort of marker to go and attach to the protein, you should be able to do a very high throughput sensing of your biological or chemical system. So that's typically the on the side of the protein, not so much on the sensor.
Also been a question regarding noise, magnetic and electric. What did you induce your noise, or you just sense the noise of the environment?
Noise of the environment. Yeah. So in principle, you can. We didn't try that. You could, in principle, generate an external noise at different frequencies and see how it responds. Generating the magnetic noise and electric noise separately, I think would be hard, given that you are only constrained by the strip line. So you can only have like the curl of the electric field and so on. And that needs to align with the exact direction of the qubit. But in principle, you should be able to also, this is something we didn't explore, and I only showed you the cases where I have either this or this, but in principle, there's also this degree of freedom that you can rotate. So you should be able to also mix them and essentially do a decomposition of the two components. So you can have a simultaneous electric and magnetic field at 45 degrees, and then you can decompose the noise. But we didn't try that.
Question about spin squeezing you mentioned at the end. My impression of that papers from Harvard, they didn't really succeed in it.
Yes.
Do you know any example where spin squeezing has been achieved?
Not in solid state. So that was the only, I think, demonstration that hinted at mild squeezing. So if you look at their squeezing parameter, they barely go below 1 with like large error bars. There's spin squeezing on the atomic physics side, obviously, but none so far in the solid state. That's the only one. Which is why we're trying to call the fact that maybe we have a persist with stronger interactions.
So in the atomic case, it's spin squeezing, or is it more
There's both.
the electromagnetic field?
So you both have like the optical as well as the spin. So in some of the work from Chila, in Adam Kaufman's group, they demonstrated spin-spin interaction, as well as from Misha Luke's group on the atomic system.
Any thoughts?
Yeah, so you mentioned using this technique to learn the Hamiltonian and then using that to derive some control sequences.
Yeah.
So you have these three nuclei that are sort of equidistant in the lattice. Is it possible to actually address a coupling to one individually, or it is?
No, go ahead.
Oh, it's that, okay.
Yeah.
Since they're sort of equidistant, I imagine their couplings are quite similar, and so then are they sort of a collective? Can they be a collective memory, or like is it possible to really address them?
Yeah, it's a great question. Naively, they're coupled. You can play the trick where you essentially, let's say, if you have your, this is your electron spin, this is your nuclear spin. You can apply a strong enough field such that all of them are pointing, because the nuclear gyromagnetic ratio is really small, so it's very easy to turn these. You can make them all of them pointing in the same direction, and that then determines how much component of control you have, for this versus like these, right? The other thing you can do is because there is a little bit of asymmetry. I mean, this was not clear in the presentation, but there is a strain term in the Hamiltonian, which then creates a little bit of asymmetry across the three spins, and you can then leverage that to individually figure out which spin you're talking to. So when I showed the plot, which looks kind of like this, in reality, it's basically a product of like N1, N2, and N3, right? So the three individual spins, right? So if you can somehow leverage that asymmetry because of the strain and then apply an external magnetic field to reorient the spins in a way, you should be able to address them somewhat selectively. Now the question is whether it's useful to do them selectively or together. It depends on the application a little bit. So yeah.